Okay, so in this next round of examples, what we have to do is actually find the simple harmonic function, and then once we have it, we can basically answer some questions. So again, we have two types. We have A cosine of omega t, or we have B sine of omega t. And basically the big difference, are we starting at a high or a low point, right? That would be cosine. Are we starting on equilibrium? That would basically be our sine, right? Based off of what we saw way back when in 4.1. So let's read the first one. So an object attached to a large spring experiences simple harmonic motion. It's pulled down, all right, 8 inches from its equilibrium. So here's what we've got. Just picture-wise, here's the equilibrium. So this mass is starting at -8, all right? Then it's released. So when it's released, we know it's going to snap back up. All right, this is over time, and then reach a maximum of 8, and then come back down, right, and just keep on going back and forth, back and forth, back and forth. So without reading anything else, I know we're dealing with a cosine, and A is less than 0, right, because usually cosine wants to start up here, but we flip through the x-axis, and I actually think I know what A is. A is -8, all right, just to kind of get the amplitude and get the fact that it's reflected. So we're halfway there. So now we need to figure out what omega is. Well, what we found is that it takes 6 seconds to complete one oscillation. So to complete one oscillation, they just told me what the period is. The period is 6. So we know that my period is 2 pi over omega. So 6 is 2 pi over omega. Cross multiply, we get 6 omega equals 2 pi. Divide both sides by 6, and it looks like omega is pi over 3. So our model will be, let's just call it S of t, is -8 cosine of pi over 3t. And so there's the mathematical model for this spring mass system, doing, all the information that we have, and matching it up at t equals to 0. Cosine is 1, so we're at -8. Right, and then if we divided 2 pi by pi over 3, we'll end up getting 6. So everything matches up pretty nicely. What's the frequency? Well, the frequency is basically the reciprocal of the period. So it's in this case, it's omega over 2 pi. So we already know that omega is pi over 3, and that's 2 pi. So we're looking at pi over 3 times the reciprocal of that, and what we get is 1/6. Okay, so we get 1/6 oscillations, I guess, per second. Alrighty, and that should make sense because it takes 6 seconds to go one complete oscillation. So we're only going through 1/6 of an oscillation per second. Alright, and then last but not least, we want to use a calculator to help us find the displacement at 6.5. So we're basically finding S of 6.5. This is -8. The cosine of pi over 3 times 6.5. So that's probably how I would enter it on my calculator. And again, I don't have my 84 with me, so hopefully this will work out real nice. So we have, I don't know where to change the sign. So I'm going to just put an 8. We know that we have a negative out in front there. And then I have the cosine, and it looks like how about I write it this way? I've got 6.5 times my pi, and I don't see there's pi, and then we're actually going to divide that by 3, right? Close my parentheses, hit my equal sign, and what we're getting is 6.928.2. All right, of course that's negative, so negative 6.9282. So that means at 6.5 seconds, as far as the equilibrium is concerned, if this is 6.5, we're down in here, we're at -6.9. So we're below the equilibrium at this time in this simple harmonic motion example. All right, so there you have that one. Number 4, this time we have an object actually moving around in a circle of radius 2. So without reading anything more, right, that means if we have a circle of radius 2, right, that means as far as the equilibrium is concerned, we're 2 and -2 respectively. All right, so and then we're going to be oscillating back and forth between all that. So I know right away that A is equal to 2, maybe negative 2 depending on other situations. We're also told that the angular velocity is 3 radians per second. So I just basically told you what omega is outright. Okay, and then it doesn't really tell us, I'm sorry about that. Let's just assume that we're starting on equilibrium just so we can be different here. All right, and so if we start on equilibrium, that means I'm starting here and then going up to 2 and then back through equilibrium down to negative 2 and back. So we got a sine curve. So S of t equals sum A sine of omega t. Well, my A is 2, my omega is 3, and there's basically our model to fit this wheel, all right, of radius 2 that's spinning at an angular velocity of 3 radians per second. Okay, so now that we have the model, we can answer other questions. What's the frequency? Well, the frequency is 1 over the period. So we got to find the period first. So in this case, the period, or how about we just cut to the chase? It's omega over 2 pi. And so in this case, omega is 3 and 2 pi, and there's basically your frequency. If we did ask for the period, right, the period would be 2 pi over 3. Okay, but I didn't ask for it, but I think that was just a short sight on my part. Next, I'm asking for an exact value, so no calculators allowed. So, oh my goodness, hopefully this is a special angle. So we're going to find S of pi over 3. So when I plug this in here, we get 2 sine of 3 times pi over 3. All right, and of course this is 2, the sine, the 3's will cancel out, pi. And what do we know about the sine of pi? It's 0. So at pi over 3 seconds, that basically means that I am right at 0. I'm sitting on the equilibrium. We're not up, we're not down, we're right on that equilibrium. Okay, so there's how you do some curve fitting with some word problems, if you would, in case of simple harmonic motion. It's all about finding your A and finding your omega. Sometimes we flat out give it to you. Sometimes you have to work for it a little bit, all right, with the period stuff. And that should wrap up simple harmonic motion. I think it's a great way to tie up Chapter 4 because all we're basically doing is using Section 4.1 on steroids, and we're giving things names. So we're giving them applications, which really hopefully solidifies what we learned way back then. What this also does is wrap up Chapter 4. So we're done with Chapter 4. We'll be moving on to some bigger, better ideas in Chapter 5. Again, as usual, if you need some help, you need to reach out for it. Jump on Canvas and ask some good questions. Show me some work. I'll make some corrections there. Come see me during an office hour. Make an appointment for an office hour. Whatever it takes to get the help that you need. Talk to you guys later.